So good morning, everybody. Thanks for coming to the first session. Can you hear me okay? I think so. I think probably not going to worry about it. I presume it's set up so that it's running. Okay, so good morning, and this is going to be the session on complex systems engineering. I'm Dr. Michael Zargham. I do basically engineering systems design methodology for cryptoeconomic systems and actually sort of business automation systems in general. And today I'm going to talk a bit about the concepts in complex systems and sort of lead into a broader session where we examine how this connects to crypto economy. In particular, I am sort of the mind that these things need an engineering methodology because they're public infrastructure. I'm not going to talk too much about the public infrastructure and engineering aspect of it today, but some of the other members of this session will. So with no further ado, let's talk about why these things are complex. And the first reason is because of feedback loops. We have these human, social, and economic systems that are us, and we make stuff. And that changes the nature of the world that we're in, and then we adapt to that. And this is very evident in the cryptoeconomic space because we literally see people modifying the rules of how they interact with each other. And this can be by building a new crypto network. This can be by adding a smart contract to an existing one. And we'll see some examples of that today. But sort of taking it from engineering to economics, it's important to note that we also have very real bounds on what we can design in the context of a social and economic system. And I particularly like this Hayek quote because he points out that economics' purpose is to show us the limits of what we can design. And with that in mind, we are not saying, hey, we can magically make these complex systems behave how we want them to do just because we have engineering and it magically solves these problems, but rather we're going to examine what we can and can't do with the tools, techniques, and knowledge that we have. I'd like to motivate for a moment why we have to take a complex systems sort of thinking approach to this. And for that, I'm going to refer to Zen and the Art of Motorcycle Maintenance, where it's observed that if you actually change a system by removing the thing that you don't like about it, the phenomena that's problematic, but you don't remove the sort of systemic impetus for that thing, the thing comes back. And so this is a really important reminder that we don't want to just build the same systems that we have in our conventional economy in our cryptoeconomic sort of economies. These systems that we're building, they have the capacity to be different. And if for any reason you don't like the way it works now, you might want to look at ways to use the technologies that we're creating to try something else. And that also doesn't mean that everything you try is going to work, but if you want to move forward, you have to look at not just what you're making, but sort of how it connects with the bigger picture. So today we're going to talk about the complex systems. Well, what is a complex system? Well, let's start with what's a system? Well, basically anything. Well, that's not very helpful. So we have to sort of zoom in and think about sort of what characteristics of these systems we're dealing with. And so complex systems are systems that have non-trivial interacting parts. That if you looked at all of the parts of a complex system and knew how they worked and you put them together, you still wouldn't know how the system was going to behave. And this is different from a lot of the systems that we're used to working with engineering. And even when we sort of model systems in social domains, we try to reduce them down to the point where we say, look, I've got A, I've got B, I understand A and B, I now know what I get. And when you have a complex system, you don't get that. You actually have to understand A and B and the relation between A and B, and even that, the complex system itself is more than A, B, A and B. Gets kind of messy fast. Incidentally, social systems have this property. So once we start getting into social systems, you really can't resolve them at the level of I understand the parts, and economic systems are social systems. They can have political elements, they can have financial elements, they can have sort of social elements that are like sort of human to human relationships. We do a lot of analysis on like social networks and the way people engage through our internet infrastructure. And finally, we get to our cryptoeconomic systems, which are sort of technically skeletoned social and economic systems. They have this sort of backbone of information that's durable, it provides cryptographic proofs, and generally allows us to do new things. Think of it like kind of putting up the structural scaffolding of a skyscraper. Until you learned how to build the structural scaffolding scientifically, you couldn't build a 80-story skyscraper. The reality is that the 80-story skyscraper isn't its scaffolding, it's what it was built for, what people do in it. Like, is it the office building for a bank, or is it some sort of massive art museum? Like, I don't know. It depends on what it's used for, and in fact, the community that revolves around it. So we need to think about our cryptoeconomic system sort of like this social infrastructure, social and economic infrastructure. And then with that, to get to sort of more technical terms, these systems are dynamic, meaning they evolve in time. They're networked in the sense that they actually are sort of embedded on graphs. They can be the peer-to-peer network itself. That can be the economic value flows between the agents. This can be the social relations of the parties, and in fact, many other representations. They're adaptive in the sense that not only do they change in time, but they change the way they change in time. And then they have multiple scales, meaning that you have to reason about how the system as a whole affects the incentives of the agent and how the agent's actions affect the system as a whole. So we'll talk about that a little bit more. Basic example is Bitcoin, where even the mining difficulty is defining the incentives of the miners and the miners' activities. Their choice to allocate resources to mining affects the system state, the hash rate, and in turn affects the incentive. So that's actually a pretty standard property in sort of complex systems. It's called interscale feedback. And lastly, they're stochastic, meaning they have sort of at least randomized elements in the sense of modeling. And the tricky thing is that it might not mean randomization, like you're rolling a dice or flipping a coin as part of an algorithm. It might just mean that the process that you're representing is best represented as random. Again, Bitcoin's my example here because who wins the mining reward is effectively a stochastic process, even though technically playing the proof of work game isn't random. Like, it's everyone doing this, the outcome is someone is first and they win, and you would need to model this as a stochastic process, even if the technically no one drew a random variable. So without further ado, let's talk a little bit about the network systems in a multi-graph sense. So I'm going to explore the fact that this Bitcoin example, it's got a graph with three kinds of nodes. Entities, which are people or organizations. This is our social network layer. We've got the accounts, which are addresses on chain, and we have nodes, which are computation and communication infrastructure that actually runs the network. And if you think about this in a graphic abstraction, you actually then have a bunch of different kinds of edges. And here we have entities have relationships with each other, they have controls of the keys to a particular address, and they can actually operate a node. An account can transfer funds to another account, a node can send its rewards to a particular account, and can be a peer of another node. So what I'm trying to point out here is that if you really want to understand the system of even a very relatively simple blockchain network, your minimum representation is actually 3 layers to handle the social, economic, and technical networks that appear. And I like to use this as a motivating example because some systems are actually more than 2 layers, 3 layers, right? Wasim's talk on main stage, he talked a bit about this sort of layered ontology of these systems. And in fact, a similar version of this diagram was in Claudio's talk yesterday. So now let's talk about multi-scale relationships. So in my multi-scale example, I like to sort of come to the right here and talk about what makes a practical economic model. And I'm going to appeal to the Lucas critique on the grounds that there is a dependence between the microeconomic foundation or the lower level representation of a system and the macroeconomic phenomena. And in an engineering discipline, you basically take all of your models and you say, cool, what are the parts inside of the thing that I'm modeling? What makes it up? and what is the context, what's the system it's part of, and so your model is resolved in the middle. And that can be very different depending on the thing that you're analyzing and what questions you want to ask about it. But if you can't contextualize using a macroeconomic frame and provide foundations from a microeconomic frame, there's a decent chance that you're floating off in no man's land and you really can't anchor your conclusions in reality. And the problem with this is that we do it all the time. We build stuff, we launch stuff, and then, we learn empirically later, but from an epistemological perspective, we didn't provide ourselves the foundations that we need to make strong inferences about what we observed. Taking this to the left, where I talk about the difference between possible and actual, this is a sort of trap that we sometimes fall in with statistical inference, that we see something that happened in real life, and we say, cool, that's the outcome. That's one realization of many possibilities. So a little bit like your multiverse theory, except for that we only get one of them. So we have one set of observations about what could have happened. And so in a formal systems domain, we have a separation of the concept of the realization, what actually happened, and the possible outcomes, which is the reachable space. And so that's the sort of macro phenomena that we're trying to have happen. And they're actually consequences of this sort of micros, maybe agent, maybe subpopulation level behavior that was the actual actions taken that led to the realization. But actually, when we're designing things, we're talking about action spaces. What choices can you make? So the available choices and their effects give rise to what can happen, the reachable space, but the actions actually taken and the realization, which is the sort of macro phenomenon that occurs, is the realization that we observed. And so whenever we're looking at complex systems, we have to remember that we're only seeing one realization to avoid mistakes like rolling a dice, seeing a 6, and thinking, oh man, the answer was 6. Or, in this case, if it's a 2-die pair, statistically your best bet is 7. It's not great. But the optimal strategy could be non-trivial, and the outcome doesn't tell you that you should have done the thing that would have won. This is a common trap in empirical analysis. You have to think about what you knew and could have known at the time that you made the decision, not just what you wish you had done in hindsight. For that, you reason about these kinds of structures. So in order to handle these things in practice with sort of computational experiments, basically computational social science experiments, I use structures like this. This is essentially a generalized differential equation with a opportunity for there to be external random processes, agent behavior that's totally determined by their own private signals, beliefs, and objectives, but their actions, so this is our action space, is the things you can do. The actions taken are the things that are done. They're done according to some policy, potentially private, determines what they will do given what they know and what they want. This creates a feedback loop, and in general, a computational model laps around something like this. And it does not require that we oversimplify the agents. In fact, it's sufficiently general to allow us to define a whole network of agents, maybe each with individual policies, or maybe aggregate policies. It's actually really here to understand the dynamical systems aspect, which is the fact that this loops around in a circle and allows us to emerge properties that might not have appeared if we only thought in terms of equilibrium. Now, this system could converge to an equilibrium, but it can also have non-equilibrium dynamics. It could literally have aspects that are always changing, diverging, or moving off in some unpredicted way. And we can see this when we have differential equation style models as opposed to things that pre-assume that we've achieved some equilibrium. So here's an example. It's a toy example from our tutorials on software that my team built, which is CAD, Complex Adaptive Dynamics Computer-Aided Design. It's essentially just an implementation that allows you to code up arbitrary models of the type I showed you on the last slide. This example is a network of robots that like marbles. It's pretty simple. We'll use it for training, but we can have 3 different kinds of robots. The robots are color-coded by which strategy they have. And we start adding them to the mix, and they have certain other robots that are friends, and they trade marbles. And you can see that, well, basically chaos ensues. The thing that's interesting is that we really didn't make any really complicated rules. We just basically had some robots like to take marbles, some like to give people marbles, and some of them like to have the same amount as their friends, and we get this. And in fact, I have a little video of this. And this is that system. It's a different run, but basically at every time, not only is the graph or are the marbles moving between the robots, but the actual graph itself is changing. And the point here is not so much that we can make strong inferences from this model, other than actually the dynamics that emerge are not very predictable. And when we're designing for systems, we just have to start by understanding that, trying to make reasonable assumptions and look at what is predictable, what's not predictable, how do we kind of structure the rules of the system to make some things that are important to us more predictable. So in that mind, we also recognize that these systems are going to be adaptive. They're going to change themselves in multiple ways. So here we can start with the notion of an interaction pattern. This could be the sort of rules of a smart contract that says, well, if I do this and you do that, this gets escrowed, I complete my task, someone signs off on it, and ta-da, the funds flow. Or any other set of interaction patterns. So it's the sort of rules of the world as dictated by a protocol or smart contract or ecosystem of smart contracts, and people do stuff. And so cool, this tool provides what you're allowed to do. That's our action space from before, and then people actually do stuff. And there's a feedback loop here of people doing things and continuing to move along. But what's interesting about our blockchain-enabled systems is that we embed algorithmic feedback. So when the state is in a different place, what you're allowed to do might be different. Or if you don't have a certain credential, you can't do something. If you don't have enough Bitcoin, you can't send it. You can't send Bitcoin you don't have. That's state dependence, actually. My account must have 10, we'll say sats because, well, that's all I got. And I can't send them to you unless I have them and enough to cover the transaction cost. That's embedded state feedback inside of the set of things you're allowed to do. So then we start to see this. A dynamic sort of activity changes the state of the system, changes what's allowed to happen, changes what is done. And so this system starts to have some very dynamic sort of adaptive flavor, and then you throw in governance, and you say, wow, actually in many of these systems it's appropriate and necessary for the system itself to change. And while we often exclude governance directly from the conversation of pure public networks, it's actually the case that even just negotiating between miners about whether to take a patch is a form of politics. It's a form of governance. And forking is governance of last resort in the same way that seceding from a country is governance of last resort. It's, well, I can't resolve my differences with you. We cannot agree on how to adapt or maintain the set of rules about the world, and so we're going to make our own world. And so we actually see this in things like the Ethereum fork, where there was just a complete and utter inability to resolve what the values of that community, of that social and economic system were, and we ended up with two. All right, so for the sake of showing a real system instead of just the toy example, this is the ETH-DAI pair and on a Uniswap. And so we had a couple people talk about this in Cryptoeconomics before, and what's happening here is the contract got launched and it started getting capitalized. So you can basically provide liquidity to a Uniswap instance, which is a pair of two assets, and then over time, dynamically, people make choices to do swaps based on whether they need one asset or another asset in order to just sort of transact in various smart contracts. Or they can say, hey, this is an interesting pool, and it's going to make money over time because of fees. I'm going to provide liquidity, effectively provide a service to the liquidity pool. And what I wanted to point out here is that these systems, they have a dynamical systems representation. So what you're seeing is actually a differential equations representation, or it's really a difference equation technically because they're discrete time. With the time steps being the order of transactions, from real data pulled from the actual events in Ethereum, but they're transacted on the representation of the smart contract described as essentially a difference equation in Python. and we're able to both reproduce the real activities outcomes and provide a platform then for running counterfactual analysis. Here we're seeing what returns a liquidity provider would have made in this instance, but with a representation of the contract, you can run counterfactuals in behavior, you can train models of the policies of the actors. You can say, what if I tweaked the fees? You actually can mutate the thing and ask alternative what if questions. And this is an important part of the computational social science that is required to do sort of complex social and economic systems design and analysis. So here's another interesting case. So some time ago, I'm sure people remember when CryptoKitties blew up the Ethereum blockchain. That particular project had something very interesting that is not generally talked about, and that was a reward for a birthing fee behind the scenes in the economy. So you needed to actually make a transaction for a cat to be born. And this was just a small ETH reward for whoever actually made the transaction. And without asking for it, the community really just started doing it. But not only did they start doing it, people built smart contracts to do it more efficiently. And so there was an entire market first for competing to be the first to make the call to get the reward, and then for doing this at lower cost through the sort of gas battery technique, if you know about it. And what you see here on the right is the transition from the sort of non-smart contract to the intermediate smart contracts doing the work. So you had individual accounts, and then suddenly you have this big orange blob where almost all of this activity is being done by smart contracts that didn't exist at the time the project was launched, and that this new functionality was added. And this is a form of emergence, because it's literally structure in the system that didn't exist and then sort of completed what was deployed. And this process of emergence is multi-scale in that it's not just the behavior, hey, people do these things, but even they change the shape of the system that they're doing things in by adding new composable smart contracts. And this is a pretty general property of these smart contract platforms. So I think we're going to see more and more importance around understanding not just what you deployed, but the natural closure over what you deployed, the natural things to add to make it sort of economically sort of, I don't want to say equilibrium, but sort of balanced. As soon as you have this reward, people are going to find the best ways to engage or participate with that reward. So in terms of what is realistic about actually designing, testing, deploying, operating, governing systems that have these properties, so I come from a background in cyber-physical systems. I worked on large-scale optimization and control, pandemic prevention, network resource allocation, control of cascade failures in grid-type systems. This is the kind of stuff I worked on during my PhD. So I like to point out to people that we have a field for this. We've got cyber-physical systems term coined in the mid-2000s. These are systems which have humans in the loop. They're networked or distributed. They're adaptive and predictive. There's a domain, but to be clear, no one's saying it's easy or that someone does these things overnight, but rather that the characteristics of our crypto systems are actually almost one-to-one with this graph. You have the cybersecurity elements because many of the physical systems that are large-scale infrastructure are actually military targets. So you have to think about adversaries. What is their resilience to different kinds of attacks? You need to think about cyber attacks. And as a result, the domain has got most of the equipment that we need. The big problem that I ran into when I first started working in crypto was none of this yellow and orange stuff was here. So I sort of personally created my own research group and started trying to fill it in. We know how to manage these large socio-technical systems that have some hard rules that are like the physical laws and some social behavior dynamics that we can't totally control. It's a lot of work, but you definitely don't do it without extremely high quality modeling, testing, counterfactuals, and broadly speaking, digital twins. So computational representations of those large-scale systems that you use to help understand and manage those systems. So cyber-physical systems is worth reading up on. In practice, this means that we're doing engineering now, and a lot of people jump to thinking about engineering in terms of the development and deployment of software or of other infrastructure, but it's important to recognize that engineering itself is a full life cycle thing. So it's holistic rather than part-wise. It's about synthesis. And so we have technical specialization, and we have electrical engineers and mechanical engineers and people who know fluids and people who know controls and all of that. And ultimately, those specializations are respected. People have more expertise than maybe even the architect or the systems engineer. But we pull them all together to create something that manages the complexity of the underlying system so that the user or the public is not exposed to the complexity that it takes to put up that building or put up that bridge and keep it safe. Those things are happening, they're deep, they're technical, and they actually do depend on human behavior. One of the examples from transportation systems is basically managing the effect of the roads that you built on traffic and the traffic's effect on safety. These are done with computational social science models overlaid on top of technical designs. So we really need to be thinking about these infrastructures as managing complexity, keeping it safe, abstracting it from the end user, and letting them have an experience of not having to worry about it at the same time that the engineers and scientists are making sure that it's safe for them to be using that infrastructure. And so at the end of the day, these things care about the system for its whole life cycle. You can't just deploy it and be it's not my responsibility anymore. And it's fundamentally human-centric, meaning, an engineer takes an obligation to see to the public good above the fiduciary duty, which is something that's a little tricky in a space that's driven by investors, but is fundamentally providing public good. So I'm going to run out of time. So I'm going to jump through to this slide and then more or less wrap up. So the important thing about designing and modeling these systems is that you are always making subjective choices whenever you impose an objective measure on the system. And that doesn't mean don't do it. You absolutely have to do it. You just have to acknowledge when you do it. You have to make it as explicit as possible. And so at the end of the day, we're going to imagine that we must expose those assumptions, test those assumptions, and be prepared to make changes as a result of misalignments between the objectives that we've chosen and maybe some feedback process, whether it's governance, whether it's some regulatory process that's coming from external, or whether it's just a recognition that while your system might have done what was best for you in the past, it might need to change its goals in order to continue to be a good service infrastructure for the community it's supporting. So I treat governance as a form of adaptive maintenance and think that that aspect of a crypto system cannot be ignored, although it has fundamentally different properties from the low-level protocol microcontrols up through the medium-level economic market design standardized, at least dynamic economic problems. Again, tricky new stuff here, but it's still a little bit in the historical economics domain, bent towards the more modern market design work. And finally, governance is, honestly, it's a big topic in crypto, but I don't think it has adequately been defined, and I think we're all here to help figure out what that is. So thank you very much, and on to the next speaker. We'll do questions at the end from everybody.